Hey students, this last part of the chapter is dealing with the idea that a voltaic cell, so our voltaic cell with a E of cell greater than 0, so remember that if you're setting up your cells, electrochemical cells, that the voltage has to be positive for it to be spontaneous. And the voltaic cell then, it's going to be able to give off free energy to do work. So that's the whole point of a battery, is to convert chemical energy into work. So the delta G is always negative when the E of cell is positive in a voltaic cell. And so this idea is given to us in an equation. We don't look at the derivation of the equation. But here, E of cell, if it's positive, because it's negative NFE, delta G is negative. Okay, now let's talk about what the N is. N is the number of moles of electrons transferred. So for that, you need the balanced equation. And F is a constant. So it's Faraday's constant, 9.65 times 10 to the 4 joules per volt per mole of electrons. So this is a given. Okay, if we're talking about standard state conditions, we have the symbol, the not symbol, which means that we're getting the values from the back of the book. Everything that's listed in the back, 1 atmosphere for pressures, 1 molar for solutions. Okay, so if we think about, we can quickly do one. If we have E of cell as plus 1.10 volts, because it's a voltaic cell, we can figure out what the free energy change is for that process. Let's assume N is 2 moles of electrons. Now, this is a simple equation. As I promised you, this chapter is not, the math's not hard, but it's just really understanding what the meaning of the equation is telling us, is that a battery that gives off free energy to do work, the delta G has to be negative. And then the other thing you should note is that the greater the voltage, the greater the delta G would be for that process. And I was talking while doing all this, but I do believe we get 2.12 times 10 to the 1, 2, 3, 4, 5, which would be in kilojoules, sorry. And that the bottom part here is weird, sorry. Right, because the mole of electrons cancel, the volts cancel, it would just be joules, and then we can convert to kilojoules. So hopefully that I did that right while I was talking. So the greater the voltage, the greater the voltage of an electrochemical cell, the more free energy you're going to give off to do work. So here's some important relationships. And I'm going to put a big heart by this slide. So you know what that means is for sure you're going to have questions regarding this slide on your test. That we're going to put together some of the ideas that we've had in different chapters. So we just came up with the equation delta G naught is negative NF E naught of cell. So you have a relationship there. And then from our previous chapter, delta G naught equals negative RTL and K. So these for sure you should know, correct? And then if we set them equal to each other and set them equal to each other and kind of cleaned them up, you'd end up with this third equation. So this one here is a direct equation to go from E naught of cell to K equilibrium. So in our previous question, if we're at 298, for the one that we just looked at, you could take our 1.10 volts and solve for K. And recall, let's just kind of think about this one. K here would be equal to E to the negative delta G naught over RT. And then here, K would equal E of cell times NF over RT, and all that would be to the E. I don't use that one as much. I don't know why. I mean, it's fine. In my brain, if I ever have to solve for these, I tend to find delta G and then plug in. So I do 2 steps for these, but it's perfectly fine to go in 1 step. Here's the important part for sure that you need to know. So double heart on that. Delta G naught is less than 0 when K equilibrium is greater than 1 and E naught of cell is greater than 0. That's a spontaneous cell. If you have an E naught of cell less than 0, negative voltage for the cell, it's not spontaneous. K would be much less than 1 and delta G would be greater than 0. Why is this an exciting point in our class? Is we're pulling together the entire chapter in this entire last couple of, actually, most of the chapters, right, are embodied in this chart because we started off our course early on talking about K equilibrium and what does it mean. And remember, the other part that's not shown here is spontaneous means product favored. Non-spontaneous means reactant favored. Now, the second one's there. E of cell, naught of cell is 0. K is 1. Delta G naught is 0. These would be those reversible ones that we began our equilibrium discussion, right? Where products over reactants, the ratio is 1. Okay, so really important slide to understand the relationship between all these different ideas that we've been developing over the last couple of months. So now the math part, go ahead and pause me and read this, and then go ahead and calculate. It's for the following voltaic cell, the lead and silver ion, and then you're going to calculate E naught of cell, and then find K and delta G. And remember, from what you've been practicing, the heart of the chapter is somebody has to flip here, right? You need to look to see which potential is more negative. That one gets flipped. All right, so pause me and work on the answer to this one to double check your knowledge. Okay, so you're back, and the silver one stayed reduced because it had a more positive voltage, and the lead one got flipped. So when it flipped, it changed its sign. Now I know I'm doing it a little bit differently than is shown here. What I did was flip that. So I flipped and changed the sign, so we should have gotten 0.93 volts. Recall I told you that the other way of doing it is to subtract them, but keep everything as is from the chart. And both ways are fine, but I always do them by flipping one and changing its sign and then adding. So what I'm showing is E naught reduction plus the flip naught one, adding the oxidation to equal the overall cell. Okay, so the question was, what is delta G? What is K? And so for the delta G naught, we look up here, we have 2 moles of electrons being transferred. So N is 2. You have F for Faraday's constant, and then you have E naught of cell. As expected, the process is spontaneous, so delta G is negative. One note here, what did they do? They plugged it in kilojoules. So they, just because delta G's are normally given in kilojoules, but for sure you still could have used the other value. could have used this value and then gotten the answer in joules. Okay. And then lastly, using this equation, they solved for K equilibrium. When you're solving for K equilibrium, you want to realize that ultimately you have to take the anti-log or anti-ln. Now, there's something interesting about this slide. So I just want to go back to the previous one to clear something up. And a lot of books do this. Go back. If you notice, E naught of cell equals RTNF ln K. And there are some books that convert that to a log, and they don't tell the students. So they're like, oh, let's just switch to logs. So keep in mind that I'm just going to start it from here, and I would have plugged in, well, I can tell you what I would have done actually is once I had my delta G, I would have done this. Delta G naught equals negative RT ln K. And I would have done this. K equals E to the negative, negative delta G naught over RT. So that's what I would have done. And I would have gotten this answer here. Or you could have solved for K. K equals E to E naught of cell NF over RT. I don't know why these guys switched to log. It's very odd. So I'm going to just say, yuck. Why confuse that? Okay, but you should get the same answer. I also, more than anything, want you to notice how big this number is. So voltaic cells at around 1 volt are giving off a lot of free energy and are extremely product favored. So we will see this. This is going to be kind of a thing for these voltaic cells, that the numbers for K equilibrium are massive. Okay, our last section is Nernst equation, and for sure you're responsible for Nernst on your exam. Let me tell you something that's not shown here, is that the Nernst equation is derived from our equation from last chapter, this guy. How are they derived? Is delta G is equal negative NFE so we're substitute. Okay, so you see how I just substituted that equation for delta G that we just went over. And then that's a big mess. So what they do is they divide through by negative NF. With that, it would end up being E of cell. E naught of cell minus RT over NF ln Q. Okay, so when we're looking at this equation, when we're looking at it, here's the interesting part is that what we've been studying, the temp has always been 298. We're not looking at other temps. F is a constant. R is a constant. Okay, so you see how everything in this pretty much is a constant except for N. Oops. Sorry, I'm a little tired today, actually. Okay, so things are going to cancel out from this. the temperature with here, the moles. Okay, so things cancel. Now, what's going to happen is that because they're all constants, you can plug those into your calculator to get a new number to clean this up. Now, if you do that, it's not going to match this number. It won't match it right now. And that's because they do that switch to convert this from ln to log. And there's a factor there, right? ln is base e, log is base 10. So they factor that conversion over from ln to log. And then you would end up with this version of Nernst equation. Now, this one's fine too. They're both okay. Which one should you use? Almost every book I've ever seen converts it over to log. So I would, when I give this to you on your test, it's going to look exactly like the one that I've circled with the little stars. And keep in mind, that's taking all of these numbers, the 8.314 multiplied by 298.15 divided by Faradays, and then the conversion factor from ln to log. That's where you get the 0.0592. What's this V? This is unit. So that's not a variable you're plugging in. It's coming, see down here where this guy has that V, it gets flipped up to the top. So the only thing you're plugging in with this then is the number of moles of electrons transferred. Okay, now I'm going to, I believe, what I want to do is erase this now, clean up this top part with all this stuff. Okay, so you have that written down, or you can rewatch it, right? Okay, that's all great, and we're going to plug into Nernst and all that good stuff. But what I really, really want you to do with this equation is really more important is what it means. What does the equation mean? Okay, let's think of the life of a battery. Okay, at the beginning of a battery, and let's pick an example, the zinc copper battery. This one should be 1.1 volts. Okay. You have a zinc copper battery. When you start a process for making a battery, the smartest thing to do would be to start with just reactants. You want to maximize your energy. Okay, now what Nernst equation is going to tell us is that when you start off, let's look at what Q is. Q would be zinc ion over copper ion. And with reactants only or close to that, you're going to have a whole bunch of copper too, correct? That's going to make Q very small. And so when Q is a lot less than 1, when you plug in a small number to here, to Nernst, that's going to make that negative. And so you're going to be adding voltage onto E naught of cell. So what's going to happen is E of cell is greater than E naught of cell. Now let's think about what that means. Delta G equals negative NFE of cell. So if your E of cell is very big because you have reactants only, you're not under standard conditions here because they're not both 1 molar, then you will have a very negative delta G, and you're going to have what we think of is your maximum amount of work the battery can do. So we did go through this in the last chapter. Do you remember? If you don't, go back and take a peek. We did this discussion before, but we did it with delta G, which is harder to visualize in my opinion. It's a lot easier to visualize with the voltages because we're used to working and using batteries all the time. So what this is saying is when you take your Duracell battery out of the package, you're at the maximum amount of work that battery can do. E of cell is more than likely not standard conditions. Your Q is less than 1, and you have all this ability to do work, to transfer electrons. So here you go. Where are we at is we're right here. This first thing, the start of the battery. The battery is going to go. It's going to give off free energy to do work. Ultimately, you're going to get to the point where zinc ion equals copper 2. And when that happens, Q equals 1. If Q equals 1, the log of 1 is 0, all this drops, and E of cell equals E naught of cell. Okay, this is that important point where you're at standard conditions. Okay, the battery keeps going. This is A, B, and C is how I'm writing it down here. When you keep the battery going, you're going to get product heavy. Zinc is going to increase. And Q will be greater than 1. Now, what does that mean in terms of the voltage, though? The voltage is starting to drop. You have less work your battery can do as the reaction proceeds forward. So E of cell is less than E naught of cell. Here's our voltage, 1.10 volts was here, right? Okay, so what is happening to our battery then? We start off with maximum work, we reach standard cell conditions, and then it's less work, less voltage. And then ultimately, what will happen is Q gets so big, this term equals this term. And E of cell ends up being 0. No more work. Dead battery. So in real life, we call it a dead battery. It really can do no more work. And then in our language that we've been talking about, this spontaneous reaction has reached equilibrium. So I know you might not like the heart thing. I'm sorry, people, but I'm going to put 3 hearts on this because this is another important part that you need to understand. You may not care so much about batteries, but remember that your generation should care because we are a generation that relies so heavily on batteries for all our amazing gadgets. So there's been what I would call a renaissance in the battery era. Batteries have been around since the 1700s, but we have all sorts of batteries now, and we need them because we have such an energy demand between our computers, our phones, our cars, etc. So the search for more effective and good batteries that are reliable is very much a priority right now. Okay. The other interesting thing is that there's a lot of this in biology and biochemistry. Our nervous system runs off of electrical signals. Our mitochondria in our cells has the process of what's called electron transport chain. It helps make ATP. Again, this is there. In fact, I just, with my introductory biochem class, we just went through electron transport and I had to go through this idea with them. So I want you to know how important it will be for whatever your majors are to have an understanding of what voltage and how it relates to equilibrium. Okay, very important discussion. So for sure, I'll ask questions regarding this particular concept. Now, there's math behind it, or there's math we can do with it. Before we get to that, excuse me, I'm going to sneeze. You're getting a very live version today of the lecture. So the relationship between E of cell and log of Q. So this is showing what I did on my little number line. You know, this one I keep drawing. This is a prettier one. You see how here at the beginning you have your maximum voltage for a cell. And then, so Q is less than 1. So E naught of cell is E of cell, is greater than E naught. Here's our E naught at 1.1 volts. And then below that, Q is greater than 1. So the cell can do less and less work. And here's our Q, the ratio of products over reactants. So let's go through this one more time. When Q is less than 1, you have more products. E of cell is greater than E naught. And that means that you can do more work in that battery. Ultimately, E cell equals E naught of cell. The ratio is 1. That's our standard conditions. This is the back of the book stuff. Please don't confuse that with being at equilibrium. That's not the case for a zinc copper cell, something that's going forward, very forward driven. Then Q gets bigger, right, as the battery operates. So E of cell starts to drop. And then eventually you get to the point where, not shown here, sorry, it's not shown in this picture. Kind of fell short of getting to that point where E equals 0, you reach equilibrium. Okay, and it's at this point, let me show you that. So here's our Nernst, right? Okay, let me show you something then. At equilibrium, E of cell, this one, non-standard, is 0. And then that's where we can set these guys equal to each other. And if we're at equilibrium, I can change it to K. So if you go back to the slide, remember this is another way of, or this is an equation we can use to solve for K equilibrium. This is the same one that was in the previous slide, a couple slides back. The difference here is that this was, the 0.0592 was derived at 298. And it's plugged in there. The V again, sometimes I'm kind of lazy and I don't even write in the volt part because I don't want it to confuse you guys. That's just a unit. So you're not plugging anything in for there. So that, in other words, so that you get your E naught of cell comes out in volts. And it's a derived unit. Okay, so I'm going to put C previous slide. So this, again, is a recap of my diagram on the previous one. Super important in concept to understand voltaic cell. We could, if we wanted to, do a calculation with this. There's some in the lab, the new lab that you are working on for this. But let's say we want to know for our zinc copper cell. We'll keep things simple. What is E of cell when the concentration of copper 2 is 0.20 molar and the concentration of zinc ion is 0.0935 molar? Okay, when you see that these concentrations are not standard conditions of 1 molar, then you know that you need Nernst equation. And we would have had to calculate E naught of cell. We've been using this value for a while, but that would come from what we've been practicing, right? You go to the standard reduction potential chart and flip one. The number of electrons is 2, and then we take the log of product over reactant. Now, let's see where we're at. Q, you can correct me if I'm wrong, doesn't have that many sig figs, but Q I got as 0.46. So Q is less than 1. So if we think back to our chart that you need to know, E of cell should be greater than E naught. And what happens is this whole mess is a negative number. So you're going to take 1.10 volts minus that negative number. So it should add on to it. Now, I'm not going to lie, it's not a big add here, I can tell you right now. I'll explain why in a second. It barely changed it because we're not that far away from Q being 1. Okay? So that's one type of calculation, very straightforward. Another thing I could ask you, it would be if E of cell is 0.56 volts and the copper ion concentration is 0.0032 molar, what is the zinc ion concentration? So if you note, the E of cell is lower than E naught, so the battery's starting to die off here, correct? So we can plug in our values. Oops, sorry. We have product zinc, okay, and so we're going to solve for the zinc ion concentration, very standard question. So if we rearrange this thing, you would take, I'm kind of out of room, but we'll do it tiny. Well, maybe not. 0.56 minus 1.10 volts, right? So we're going to get negative 0.54. Okay, so negative 0.54 volts, and then I'm going to multiply by 2, divide by negative 0.0592. Then I'm going to have to take the anti-log of that and then multiply by 0.0032 molar. That will get me my zinc concentration. I'm working on it. So the number you're going to get is going to scare you. It's huge. It's massive. But remember, we'll look at the picture here in a second, but the voltage is getting smaller, which means that you're heading towards equilibrium, and you're going to have a very large amount of product, right? As we approach equilibrium, remember that the ratios get big, 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 because it's a very spontaneous forward reaction. So it's not a big surprise that this is a large number. And we can double check ourselves on our math because, I was talking. Yeah, we're fine. Okay. So going back to this slide, where are we at? We're down here where the ratio is super large. Q, is a lot greater than 1. So the voltage is less than E naught of cell. That's what we saw when we did that question, was that the voltage was less than E naught. So Q is getting very, very big. Okay, you're heavy on products. Okay, so there's a couple more things. This next part is really to give you a good understanding of all the different kinds of batteries. I don't ask questions on this, but there is one slide coming up, so you need to hang tight. There is one more slide that is important for your exam, but I do want to make this as close to a real class and real lecture as possible. So I would have gone through this because I think it's just important to understand the different batteries you guys work with in real life. But I'm not testing on it, but I just want to show you them. So bear with me. Alkaline batteries are zinc, manganese dioxide. Obviously, we don't run around with beakers and salt bridges, but all of that is included in here. It's just that they tend to be solids and pastes that they put in there. And the oxidation here is zinc, is the anode. The reduction is the manganese dioxide. The other thing I think is important that I mentioned to you in an earlier video is that redox love either basic or acidic environments. And this particular battery likes base, so that's why they're called alkaline batteries. There's still a redox. The anode transfers electrodes to the cathode through a wire, and that creates that voltage that we rely on. Again, delta G is negative for these because we want these to do work. So you've seen those silver button batteries, similar, except that the cathode in this case is a silver oxide, so Ag plus going to Ag element. So same idea, but a different different cathode, still basic. The voltage of this cell is 1.6 volts. So these are more lightweight, smaller batteries because they tend to be used a lot in watches. Lithium battery, my favorite, really reactive battery, sort of the new wave in terms of technology, very temperature sensitive because the lithium's so reactive. So as we know from our cell phones, we have to be careful to keep them stored in a more cool environment. but a very high energy to mass ratio. So in other words, you get a lot of electrons, a lot of electron flow from a very small amount of metal. It's difficult to find lithium uncombined in nature, so they have to process salts to get the lithium out, and that then adds a whole other process to this that makes it adds cost to these batteries because they're more expensive. My least favorite battery is the lead acid battery from your car. And the reason why I don't like these is because lead is a toxic, nasty element. And it's amazing that we've stuck with this battery for so long. But the anode is lead. It's in the presence of a very strong acid, sulfuric acid. So that's why there's all the warning labels to be careful with the car battery. And then the cathode is lead 4 oxide. And so overall, the cell voltage is 2.1 volts. That's not enough to power the electricity in your demands of your car. So a car has 6 of these. And so then you're up to around 12 volts with 6 of the cells put together. Another one, nickel metal hydride battery. So you can have other metals. If you're noticing, the issue of disposal of these is important because these are metals that you don't want in water supplies. So, and that's also a discussion. If we had more time and we were in class, we'd talk more about the lithium batteries because, my electric vehicle is powered from lithium batteries, but they do present an environmental discussion there as well because my car is something like 192 lithium batteries. So that's an environmental discussion. So I think later, as you move forward in your careers, that science has these incredible things we do, but there's always a price that's paid for technology. And in the case of these batteries, for sure, it's their disposal. They present environmental hazards. Here's the lithium ion one. I believe at some point I mentioned it's super ridiculously complicated. And so you can see that here, very complicated anode and cathode, but very high in energy with 3.7 volts. Fuel cells, you've probably heard of those. It's another way of generating electricity. The anode in that case is hydrogen gas. The cathode is oxygen. And it's interesting because the overall reaction is hydrogen plus oxygen to make water. So the product's really nice. It's not the nasty metals that create environmental hazards. Hydrogen fuel cells have been used a lot in spaceship technology. Okay. But the problem is the hydrogen gas, flammable. So these were, gosh, I want to say 15, 20 years ago, trying to get pushed a lot into thinking about using them in vehicles. And there was sort of this negativeness with that due to the idea that you had hydrogen in your car. What's going to happen if you get in a car crash? So, anyways, there was, but this type of technology is used a lot in spaceships. Okay, lastly, you do need to know this by definition of what an electrolytic cell is. And if you go back, one of the first diagrams I showed you in the previous video lecture was a diagram that showed a comparison of galvanic versus, or voltaic cell versus electrolytic. So this is going to be an important slide as far as definition goes. An electrolytic cell is not spontaneous. It needs an outside source of energy to drive the reaction. So E naught of cell is negative, delta G is positive. So now the voltaic cell, oxidation still occurs at the anode and reduction still takes place at the cathode. But because you're supplying an outside current of electricity, for the reduction, then the cathode is negative. Excuse me. So that's the difference. And there should be a picture on the next slide. Oh, here's the one that I wanted to show you. Great. You have here's a tin copper battery. This one on the left side would be the way that you generate a voltaic cell. For a voltaic cell for this, tin wants to oxidize, copper wants to reduce. Okay, the voltage E naught of cell is 0.48 volts. And E naught of cell on this side is negative. It's a negative value. So in this case, the voltaic cell, the electrons will spontaneously flow from the tin towards the copper. The other direction doesn't want to happen. The copper doesn't want to oxidize. The tin does not want to reduce. So you have to put a current of electricity on here. And so you have an outside source of electrons. And that's why the cathode is negative, because you're applying an outside current that's forcing that side. So here's the reduction side. You have to add those electrons in, and so that makes the cathode negative and the anode positive. Okay, so maybe you're asking yourself then, if these are a hassle, why do we need to know electrolytic cells and concept? Is the idea that I keep using the example, your cell phone at night, after it's dead, you want the reaction to go backwards. That's not a spontaneous reaction. So you have to put an outside source of electricity on it. This is showing that idea with your recharging a lead acid battery, that the flow normally, right, is going to go from here, the anode being negative, cathode. So this is your voltaic cell. But if you want to recharge the battery, you have to provide a power supply of energy to force the reverse reaction to happen. Okay, so it is an important thing, because in real life, we try to recharge a lot of our batteries. And then also another place this comes in to play is it's how we make elements from compounds. So it's not shown here, but if you want to take, let's say, water and form its elements, that we have to apply an outside current. And this is called electrolysis. And it's definitely a huge discussion in industrial chemistry, how we can make reactions happen that are non-spontaneous. Okay. I would know this for sure as just a multiple choice question that'll be on your test, just in concept, the comparison of voltaic and electrolytic cells. There are calculations that can go with this, stoichiometry of electrolysis. We don't have a lot of time for this, so I won't be asking this part, but as far as the question goes, but it's the idea that in electrolysis, let's see if there's a picture.